I'm making heart love, hug waffles today from scratch. These are gonna be delicious. And there you go.
Today we're going to be using chemical energy for our challenge. And we're going to be making a tomato basil infused foam with a tiny bit of corn chowder. In molecular gastronomy, foam is huge. Everyone loves foam. That's beautiful. That's absolutely beautiful. Molecular gastronomy.
Today, Chef, I made some sparkle love heart waffles.
Oh yes, my Skylar. That is probably one of the best waffles I've ever eaten in my entire life.
Today, Chef, I made you a tomato basil infused foam using molecular gastronomy with a tiny corn chowder.
Foam? Foam? You make it to the Top Chef finale and you give me foam? Well, after trying out both dishes, the chef who will be leaving us tonight is Xassel. Please pack your knives and go.
Yes!
Congratulations, Skylar.
Yes!
You are the winner of Top Chef Season 18.
Yay!
I'm really devastated right now. I can't believe that the chef did not choose me. I'm a trained chef. I'm a professional chef. I worked with molecular gastronomy for about 2 years now, and I just don't think the chef appreciates that. You know what? I'm just done.
I can't believe I won. This is the best day of my life. I think I might have to start serving my own breakfast restaurant because I know how to make eggs and waffles.
Hi everyone, welcome back. I'm so glad that Skylar won the cooking challenge. Go Skylar. She has some tasty maple syrup on board, which is a type of chemical energy. Alright, so we're going to continue with our topic on energy, and we're going into lab 2, renewable and non-renewable energy. Our focus question today, what types of energy do not harm our environment? And we're looking at either renewable or non-renewable use. So let's first discuss what an energy resource is. An energy resource is going to be something that we use to get energy, to either fuel our cars, heat our homes, and power our cities, and numerous other things. Here's two charts of what a renewable versus a non-renewable type of energy looks like. In the renewable category, we have solar energy, we have wind energy, we have water energy, geothermal energy, and we have biomass energy. On the non-renewable energy side, we have coal, we have natural gas, we have oil, we have nuclear reactions, and all of those again are going into energy use that we use every day. Both of them do. Let's focus on renewable energy. So if we take a look at this pie chart, we can actually see what the U.S. consumes in terms of energy consumption for 2017, which I at least have found is the most up-to-date information. Please note that the majority of energy consumption is actually in the non-renewable category, whereas we only have about 11-ish% of renewable resources or energy resources that we're using. So renewable resources are resources that can be replaced in a relatively short amount of time, and it produces very little waste products, which is a big deal. Please note that these are used daily worldwide, but again, not as much as non-renewables. Some examples of these include wind turbines to harness the wind power, using solar panels to harness the solar energy from our sun. So let's focus on solar power. Solar power is, of course, taking the energy, which is, again, if you remember from our last lab, nuclear energy, which is a fusion reaction in our sun. So it's kind of like the biggest nuclear reactor we can have. And taking that and transforming it into electricity with solar panels. And many people have them on their roofs, so when the sun is out, they can gather that energy and convert it or transform it to electricity and use it in a day-to-day use. Let's watch our good friend Bill Nye shed some light on solar panels and solar energy.
On the other side of this roof, the energy of the largest thermonuclear reactor in the solar system is beating down. But we can harness that energy. We can harness the power of the sun. We haven't begun to tap the sun's energy. Right now, more solar energy hits the Earth in a day than everyone on Earth could use in 27 years. Currently, we tap barely 1% of the sun's power. If we could take all the energy and all the fossil fuel on and in the Earth today, it wouldn't equal the amount of energy that comes from the sun in just 20 days. Hence, this solar array. In 1954, scientists discovered that silicon, the same material that beach sand is made of, if it has just the right impurities in it, will produce electricity when light hits it. A battery like this makes about 1 watt's worth of electricity. Each of these panels produces about 180 watts. In this system, there are 24 panels, and we get about 4,000 watts under perfect sunlight conditions. That's 4 kilowatts. It's not bad. This meter shows how much power the solar panels are producing. On a bright sunny day like this, look how fast it's going. Most days, this electric meter runs backwards. Here in California, the Department of Water and Power gives you credit or buys back your excess electricity. Now, that's not just a good idea, that's a law, a federal law. This little gizmo does a big job. It converts the direct current, or DC, from the solar panels into alternating current, or AC, which ties into the American electrical grid. And the average American household produces the equivalent of about 10,500 pounds of CO2 every year. So this system, with the solar panels and this inverter, have saved the equivalent of 14,777 pounds of CO2 in the last 15 months. You gotta feel pretty good about that. How much does a system like this cost? Well, anywhere from $10,000 to over $50,000. That sounds like a lot of money, but remember, many states have rebate programs, low interest loans, and tax incentives. So that brings the cost way down. So next time you're in the attic, think about what you can do on the other side.
Thanks, Bill. That was great. All right, let's focus on another renewable energy type, wind energy. And if you live in North Kingstown, you're probably familiar with that great big wind turbine next to Walmart. And that is definitely using the wind's motion to convert mechanical energy of the gears inside the wind turbine into electricity that's going to National Grid and helping to power our homes. So wind power is a big deal in terms of clean energy, renewable energy. The wind is always going to be blowing, and it's something that you put one up, you put a few up, you're going to get a lot of energy in a relatively short amount of time. How about water energy? They also call that hydropower. Hydropower, a little bit more complicated to use because everyone does not have access to a large amount of water. Here's an example of the Hoover Dam, but that's in Nevada, Arizona border. So people in that location can definitely access it, along with other locations that have access to a dam and water, moving water. Now, this is a really interesting resource because this is the most widely used form of renewable energy. So even though there are not dams everywhere, the energy that it creates in terms of transforming the moving water energy to electrical energy is a lot. You can generate a lot of energy, and it can be transformed over to many different locations around that area. So let's take a look at inside a hydro power plant. And You can see this animation, how the process of taking water from stored water in a reservoir goes through that dam and makes it so its way to the generator, and eventually it gets transformed to energy that is going through power lines to make sure that everyone is able to access electricity in their home.
Hydroelectric power plant. In a hydroelectric power plant, electricity is produced from water. A dam is built across a large river to hold back the river water and raise its level to form a reservoir. At the bottom of the dam, there is a floodgate. Water flows through the penstock and rotates the turbine. The flowing water rotates the turbine, which is placed at the end of the penstock. The turbine, in turn, rotates the shaft that is connected to the coils of a generator. These coils are placed in between strong magnetic poles. The rotating shaft turns the coils. The change in magnetic field due to the movement.
Okay, another type of renewable energy that many people may not be familiar with is biomass energy. That's through natural products being burned or gas collection from its natural products decomposing over time. And that can actually be used for energy, believe it or not. We use crops and things of that nature to help us generate biomass. Okay. Let's focus on non-renewable resources, which is, again, probably what we're more familiar with on a day-to-day basis, which is a resource that exists in a limited supply. And these non-renewable resources can unfortunately cause some pollution when they're burned. It does take millions of years of these non-renewable resources to form again. So once they are burned, once they are used, we can almost say that they are no longer available. So those fossil fuels, that's what we call them, because again, millions of years of time it took to make coal, oil, and natural gas with different kinds of natural materials, plants and animals that were extinct millions of years ago to decompose and to eventually get pressured down into the earth, so much so that it formed those different resources. Again, once they're used up, unfortunately, they are no longer accessible. So with coal, it's compacted matter that's dug up from the Earth's surface and burnt. And please note that it's a good type of energy use, but again, once it is consumed, all of those reservoirs are no longer accessible to produce more energy. Natural gas is again found under the Earth's surface. All of these are underneath the Earth, and again used to produce energy by burning it. Please note all of these need to be burned, so they are going to give off some pollution and exhaust that can impact our environment with carbon dioxide gas. The last one we're going to focus on is nuclear power. Nuclear power plants make it and utilize the element uranium. Now, uranium is radioactive, and it can generate great amount of heat, which can turn a turbine, and which is the steam from hot water that's being heated, turn a turbine, and generate electricity in great massive amounts, which is wonderful. But again, there is some questionableness about the way that it goes about doing that. So let's take a look at how a nuclear reactor works.
Nuclear reactor. In this video, we're going to learn about the nuclear reactor. Nuclear reactors are the modern-day devices extensively used for power generation, as the traditional fossil fuels, like coal, are at the breach of extinction. A nuclear reactor is the source of intense heat, which is in turn used for generation of power in nuclear power stations. Its mechanism is similar to that of a furnace in a steam generator. The steam is used to drive the turbines of the electric generator system. A nuclear reactor consists of three crucial components: fuel elements, moderator, and control rods. Fuel elements come usually in the shape of thin rods of about 1 centimeter in diameter and contain fissionable nuclei like uranium-235 or uranium-238. These rods vary in number according to the size of the reactor. In large power reactors, thousands of fuel elements are placed close to each other. This region where these fuel elements are placed is called the reactor core. These fuel elements are normally immersed in water, which acts as a moderator. The objective of a moderator is to slow down the energy neutrons in a nuclear reactor, which are produced during the nuclear fission process by the fuel elements. Thermal neutrons, which are the neutrons with energy of about 0.04 electron volts, are capable of producing fission reaction with uranium-235. During the fission reaction process, new neutrons are given out, which have energies of about 1 MeV. This is 1 mega electron volts. These neutrons typically escape from participating in another fission process, as they are accompanied by enormous energy release. In fact, the probability of these neutrons produce another fission reaction is 500 times less than that compared to a thermal neutron. This is where a moderator is extremely useful. Moderators have the capability to slow down, or in other words, moderate, the speeds of these high-energy neutrons so that they can in turn be used for a chain reaction to trigger multiple fission reactions of other uranium-235 nuclei. Commonly, ordinary or heavy water is used as a moderator in nuclear reactors because of the deuterons present in them, which are capable of slowing down the neutron speed. Water molecules in the moderator are useful in slowing down the high-energy neutrons, which leave the fuel element after nuclear fission. These high-energy neutrons collide with water molecules, thereby losing out on some energy with every collision and therefore slowing down substantially. A new fission reaction can now be triggered using this slow neutron by striking it with a fuel element. The third and most prominent part of a nuclear reactor are the control rods. In order to get a steady output of energy from the nuclear reactor, every single fission reaction should trigger another fission reaction and ensure the availability of spare neutrons released to trigger the chain reactions. By controlling the number of spare neutrons available at any given time, the rate of nuclear fission chain reactions can be controlled. This control on the fission reaction can be maintained using control rods. The main function of the control rods is to absorb any excess or spare neutron in the moderator in order to prevent any further fission reactions. Usually, such control rods are made of boron or cadmium. To increase the rate of fission reactions, these rods can be removed from the moderator. A steady output of energy can thus be maintained by inserting or removing the control rods in the nuclear reactor. Now that we know the components of a nuclear reactor, let's understand the working of a nuclear reactor. It's usually enclosed in a shield made of thick concrete walls. It consists of a reactor core, pump, and heat exchanger. The reactor core and pump are placed in contact with the water, which is usually the heat exchanger in these reactors. Due to the enormous amount of heat released during the fusion reaction, the surrounding water gets heated up and changes to steam, which is in turn used to turn the turbines. So, huge heat energy gets converted into electrical energy. Water is continuously flown in and out of the nuclear reactor using the pump. So, a nuclear reactor successfully generates nuclear energy from fission reactions.
Okay, so uranium is placed into those long tubes and placed into water to make sure that it can bounce off of water molecules and stop how fast the neutrons are going, which is a good thing, to stop that chain reaction if needed. So please note that it does release tons of heat. Again, it heats the water produces steam or becomes steam as a phase change, and that steam can power a turbine or a rotation to produce electricity. Okay, so with all that information, I'm going to ask you to bring it to the energy transformation gizmo. And the gizmo has some really nice transitions or sequences from one type of energy to the next. It does include solar power, wind power, and biomass, and it is going to ask you to identify those types of energy within it. So please go ahead and complete that portion of your Lab 2, and when you're finished, please submit it by this coming Monday. I'm going to ask you to, just double check also that you have turned in your work for our third quarter, which might include a quiz retake if needed, and that way everyone's on the same page. You will get the grade that you should get because all of your assignments are in, which is a big deal. Okay, if you haven't already done so, please subscribe to the channel, and I hope you have a great rest of your day. Take care.